Hello everyone, in the lecture today we will learn combined measurement, which will use stadium to complete the measurement of horizontal and vertical distance and vertical angles at the same time. In surveying, the stadium measurement is one method to determine both distance and direction at the same time. In the figure on the right, you can see that by reading from the stadium rods R1 and R2, we are able to find out the horizontal and vertical distance, and also we can read the vertical angles directly from the instrument. This method is very convenient for traverse and leveling measurement, and also it could be applied to complete the location measurement for topographic surveying and leveling and field completion surveying. Actually, for many surveying instruments, such as transit and satellite, their telescopes comes with both cross-airs and stadium airs. The two figures here shows two different types of the stadium airs. In general, the stadium airs will be applied at the top and bottom of the telescope, and their distance to the center of the crosshair are the same. In the measurement, we will try to check the interval read between these two stadium airs, and this interval will be applied for us to estimate both horizontal and vertical distances. The stadium method, we actually need to apply stadium rods in the field experiment to read the information and estimate the distances. The figures here demonstrate 4 different types of stadium rods applied in the field experiment with different units. From figure A and figure B, we can see that usually with the stadium method, we will have 3 readings from the stadium rod. That would be the reading from the cross L, and the reading from the top stadium L and bottom stadium L. We will need to use the information from the cross L and the interval between these two stadium airs for the estimation of the horizontal and vertical distances. Now let's see how we can apply the stadium method to measure the distance. The figure here demonstrates the horizontal side applied in the stadium method. Here the line of the sight from the telescope is horizontal and the stadium rod is vertical. In this figure, the stadium L is located at point A and B in the instrument, and the apparent location of these two stadium L in the stadium rod is measured at point A and B, and the interval between these 2 points is set as little s. In addition, we know that the interval between the two stadium L is little I. And then we can use this information to find out the horizontal distance from the instrument to the stadium rod, that is capital D. So we want to find the value of D. From the figure, we can also see that the principal focus point of the telescope is capital F, and we define the distance from the point to the telescope as letter F, and from the edge of the telescope to the center of the telescope as little c. As the telescope is in a cylinder, we can assume that the distance between AB and A prime B prime is the same, so we have AB equal to A prime B prime. Also, due to the principle of the similar triangles, we can get F over I is the same to D over S. So we assume that these two triangles are similar to each other. And with that, we can derive that D equal to F over I times S. Here, letter F and I are all the features of the instrument. So we can assume that the value of F over I is a constant and it's the feature provided by the instrument. So letter D equal to K times S. And with that, we can get the horizontal distance measured from the instrument to the stadium rod as little d plus c plus f. That is k times s plus c plus f. And we assume that the second part is in a constant value. This one is also in the feature of the instrument. So based on the given instrument, we know the value of capital K and the value of capital C. And we are able to read the value of S. And with that, we can find out the horizontal distance. The stadium method can also be applied for inclined sign to measure both horizontal and vertical distances. The figure here demonstrates the principle of the measurement of these two distances. Basically, from the previous analysis about the horizontal side, we can get the sloping distance from the center of the instrument to the reading of the cross L, E, that will be di equal to k times a prime b prime plus capital C. Here both k and c are given, which will be the constants from the instrument. However, in the real experiment, you cannot read a prime b prime. So a prime b prime unknown. Instead, you can find the value of ab, which can be read from the stadium rod. However, AB is not the same to A prime B prime as shown in this figure. So we need to find out the relationship between AB and A prime B prime. Here we have to make some reasonable assumptions. First of all, we need to assume that the angle here, which is beta is very small. And then by this assumption, we can derive the second assumption, that is EB prime is perpendicular to FB, and EA prime is perpendicular to FA. With these assumptions, we can then derive the relationship between the intervals read from the rod and the horizontal and vertical distances. Now let's see how we can use this information to find out the horizontal and vertical distances. Actually, in an experiment, the instrument can also measure the vertical and zenith angle. That will be alpha and z in this figure. In addition, from the figure, we can find that the angle of B, E, and B prime, which would be the angle here, is the same to the angle of A, E, and A prime. That will be the angle here. And they are also the same to the vertical angle. Similarly, it's also the same to 90° minus zenith angle. And we also know that A prime B prime equals to EA prime plus EB prime. And from the assumptions, we know that EB is perpendicular to FB. At the same time, EA prime is perpendicular to FA prime. So we can get EA prime is AE times cosine alpha, and EB prime equals to BE times cosine alpha. So that is AE plus BE times cosine alpha, which is AB times cosine alpha. So with that one, we can find that the sloping distance, capital DI, equal to k times s, that's the value of AB, times cosine alpha plus c. And it's also the same as k times s times sine z plus c. And then we can derive the horizontal and vertical distances. For the horizontal distance, capital H equal to d times cosine alpha. That is k times s times cosine alpha square plus c times cosine alpha. This is also the same to k times s times sine square z plus c times sine z. And then for the vertical distance, v equal to d times sine alpha. That is k times s times cosine alpha sine alpha plus c times sine alpha. This one is equivalent to half of k times s times sine 2 alpha plus c times sine alpha. So that's the formula for us to use the interval read from the stadium method to estimate the horizontal and vertical distances. For the real-world implementation of the stadium method, based on the reading from the experiment, we can apply some approximation to the horizontal distance estimation. For example, if the vertical angle is very small, that is, if alpha is less than 3 degrees, then we will have cosine alpha is close to 1. In that sense, we can simplify the horizontal distance as k times s plus capital C. And we don't need to worry about the vertical angles. And in addition, due to the unequal refraction and accidental inclination of the rod, sometimes we can ignore the value of capital C. So that will give us the simplified equation as capital H equal to k times s times cosine alpha square. And the vertical distance is half of k times s times sine 2 alpha. So that's two approximation of the stadium method. For the stadium method, the value of capital K is very important for us to estimate the horizontal and vertical distance. However, sometimes the value provided by the instrument may not be accurate enough, so we have to apply some calibration to find out value of capital K. For the calibration, we will usually apply some known distance and try to find out the K values for each measurement, and then find out the average value of K to calibrate their values. So in the calibration, we will place the instrument at one location and point the instrument to some given locations. Say it's P1, P2, P3, P4, and we place the rod at these locations. And then we will have the readings from all these rods. Instead, we will have S1, S2, S3, S4, and so on. In addition, we are given the distance to all these points. To P1, say is L1. To P2 is L2. P3, L3, P4 is L4. And then we can call the definition about the horizontal distance from the stadium method. Here we actually put the instrument and align the line of sight horizontal. So we will have L1 equal to K times S1 plus C, L2 equal to K times S2 plus C, L3 equal to K times S3 plus C, L4 equal to K times S4 plus C. As the line of sight is horizontal, we have alpha equal to 0, which will give us this simplified equation. And with this simplified equation, we can find out the value of K for each scenario. And then we can calibrate the K value as K bar equal to K1, which is from the first equation, K2, K3, K4 over 4. And this average value will be used for the stadium method for this specific instrument. Now let's take a look at one example for the implementation of the stadium method. In this example, we assume that a set of data was obtained from the experiment. We know the zenith angle is 81 degrees 50 minutes, the interval is 2.5 feet, and the stadium interval factor is known to be 100 and capital C is 0.75. It wants us to find out the horizontal and vertical distances. So first of all, we'll try to summarize all the conditions. So we have the stadium interval as 2.5 feet, and the zenith angle is 81 degrees 15 minutes. Also, we know capital K is 100 and capital C is 0.75. And we want to find out the horizontal and vertical distances. Then for the solution, we can start with the horizontal distance. We know that horizontal distance is K times S times sine square zenith angle plus capital C times sine Z. That is 100 times 2.5 times sine square 81 degrees 50 minutes plus capital C, that is 0.75 times sine 81 degrees 50 minutes. So the answer is 245.7 feet. So that's for the horizontal distance. For vertical distance, we have half K times S times sine 2 alpha plus C times cosine alpha. Here alpha is the vertical angle. Alpha equal to 90 degrees minus zenith angle. In this case, that will be 8 degrees 10 minutes. So we have the value as half 0.5 times 100 times 2.5 times sine 2 times 8 degrees 10 minutes plus 0.75 times cosine 8 degree 10 minutes, which will give us the result as 35.3 feet. So that's the way for us to calculate both horizontal and vertical distance with the stadium method. Now let's check a second example. Here we know that the stadium interval was 1.372 meters and the vertical angle is 20 degrees 32 minutes. Capital C is 0.3 meters and the stadium interval factor is 100. It wants us to find out H and V. Similarly, we need to summarize all the conditions are given. So we have S equal to 1.372 meters and the vertical angle alpha equal to 20 degrees 32 minutes. Capital C is 0.3 and capital K is 100. It wants us to find horizontal and vertical distances. So in the solution, we will call the formulas for the capital H and V directly. H equal to K times S times cosine alpha square plus C times cosine alpha. That is 100 times 1.372 times cosine 20 degree 32 minutes square plus 0.3 times cosine 20 degree 32 minutes. So the result is 120.6 meters. And then for the vertical distance, it equals to half of K times S times sine 2 alpha plus C times sine alpha. That is 45.2 meters. So that's a different way for the calculation of horizontal and vertical distance with vertical angle. Now let's see how we can use the stadium method to find out the elevation difference between 2 points. The figure here demonstrates the procedure for the elevation difference estimation. First, we'll place the instrument at the point A, and then we place the stadium rod at the point D. We will then apply the instrument and use the stadium method to find out the vertical distance, which is the vertical distance from the point E to the center of the instrument. And we want to find out the vertical distance of the points A and D, which we say is VAD. From the figure, we can see that VAD equal to AB, which is the height of the instrument, plus CD, which would be the vertical distance from the center of the instrument to the point of D. And we have AB equal to the height of the instrument, and we also want to find out CD. CD actually equal to CE minus DE, and CE is actually the vertical distance made from the stadium method, and that is V minus DE. From the figure, we can see that DE is actually the reading at crosshair, and we also can find out capital V, that vertical distance, as half of KS times sine 2 alpha plus c times sine alpha. With that, we can derive VAD as the height of the instrument plus half of Ks times sine 2 alpha plus c times sine alpha minus the reading at the crosshair. So that's the way for us to find out the difference in elevation with the stadium method. We can also apply the stadium method to find out the elevation difference at two given locations. For example, in this figure, we want to find out the elevation difference between point B and F with the stadium method. To get this value, we will put in an instrument between B and F and apply the backside to a rod applied at point B and the foresight to a stadium rod set at point F. And we want to find out the true elevation difference, which would be the vertical difference between B and F. From the figure, we can see that VBF is actually equal to the length of AB plus the length of DF. We also see that AB equal to the vertical distance at the backside VB minus the reading at the rod, that is BC. For DF, that actually equals to VF plus EF. EF is the reading at the stadium rod. We know VB and VF can all be calculated from the stadium method. VB equals to a half of K times the interval at the point B times sine 2 times alpha B plus C times sine alpha B. Similarly, we have VF as a half of K times the interval at F times sine 2 alpha E plus C times sine alpha E. So with the given information, we can then find out the value of VBF as VB plus VF plus EF minus BC. So that's the way for us to just use the reading from the stadium rod and the estimated vertical distance to find out the elevations of two different locations. The stadium method can also be applied to measure the elevation difference of 2 points which are really far away to each other. To conduct this measurement, we want to introduce the indirect leveling, where we will use some turning points for the estimation from one benchmark to another point. Now let's see how this work is conducted. Assuming that we have a set of the points we want to measure, we know the benchmark, and we can set up a set of turning points and eventually we can get to the target point. To conduct this kind of experiment, we will place the stadium rod at the benchmark and turning point 1, and then we will set the instrument in between. We have the reading at the turning point 1 and benchmark 1. So this is a back side and this is a foresight. And then we can set another stadium rod at turning point 2 and place the instrument in between. We will have another backside and another foresight. Similarly, we can extend this process to many other locations. For each one, we will have a backside and a foresight. We will also read the vertical angles or zenith angles at each side. And then we will use this information to find out the elevation difference between the target point and benchmark. The table here shows the note of the indirect leveling with the stadium method. Basically, for the backside, we need to record the interval from the stadium rod, the zenith angle or the vertical angle, and the reading on the rod at the crosshair. We will use this information to estimate the vertical distance. In addition, for the foresight, we will record the similar information: the interval, the zenith angle or vertical angle, the reading on the rod, and the estimated vertical distances. And then for the elevation difference, we will use the reading from the rod and the vertical distance from the backside and the reading from the rod and vertical distance from foresight to estimate the elevation difference. The similar process can be applied for different turning points, and with this elevation difference, we are able to find out the elevations of each point, and eventually we can identify the elevation difference between the target point and the benchmark, and all the true elevations of the turning points. So that's all about the lecture today in the combined measurement. Thank you very much for your attention, and I will see you next week for a new topic.